Welcome back to the classroom. My name is Mr. Wong, and today we'll be explaining through some exam paper questions. This one is the 2003 HSC Physics paper. It answers Module 5 Inquiry question number 3, which is all about motion in gravitational fields. This is question 17, worth 6 marks. We have a satellite that is of this particular mass here, and we launch it in a uniform circular orbit of this particular radius. So the very first question says calculate the magnitude of the gravitational potential energy, and so that's all we need to do. So the formula for gravitational potential is negative gmm over r. The value for G is on your data sheet, so that's 6.67 times 10 to the power of minus 11 times the mass of Earth. So on your data sheet, that should be about 5.97 times 10 to the power of 24 times the mass of our particular satellite. Okay, and divide that by the distance of their particular orbit. So in this case here, the orbit is 7.5 10 to the power of 6 meters away from the Earth. Okay, so the radius of orbit is 7.5 times 10 to the power of 6. So that's our equation that we have there. Put in your calculator and see what you get. Okay, so we get a value of 796398000. If we want to put that in scientific notation, and we'll round it off, the lowest sig fig we used is 2. Let's try and round this off into 3 sig figs. So 96 times 10 to the power of 9 joules to 3 sig fig. So that's how you do the first one. Let's move over to question B. From this uniform circular motion, the satellite can escape the Earth's gravitational field when its kinetic energy is equal to the magnitude of the gravitational potential energy. So what that means is the potential energy of the orbit, half mv squared, is equal to our potential energy, gmm over r. Okay, so the question is saying derive a relationship to show for the escape velocity. Now the reason why potential energy here is positive is because originally the energy total is equal to potential energy plus kinetic. So if the overall change is 0, I know that potential energy is positive, kinetic energy is, or potential energy is negative, kinetic energy is positive. Move it across and you can sort of see where that positive value comes from. Okay, firstly we can cancel out the m's, so our equation looks something like so. Okay, times both sides by 2. And then we root both sides, and that is the formula for the escape velocity of an object if its kinetic energy is equal to the magnitude of the gravitational potential. Okay, question C. It says discuss the effect of the Earth's rotational motion on the launch of this satellite. So effectively, how would we want to launch it? Would we try and launch it so that it launches in the same direction of rotation or in the opposite direction of rotation? So when we launch a rocket or satellite in this case, satellite is launched in the same direction as the Earth's rotational motion. Okay, by doing this, we're also what we call assisted launch speed. We're using the additional speed of the Earth to launch our object. So our satellite will have its own speed when launched, but by including the rotational speed of the Earth's rotation in that, we actually increase that speed. Okay, this allows the satellite to be launched with the additional speed of the rotating planet allowing it to launch at a higher speed to overcome the Earth's gravitational force. Okay, and that gives you a nice little explanation of how we can derive, or look at gravitational potential energy, then look at deriving escape velocity, and why is it so crucial that we launch any form of satellite or rocket in the same rotation as the Earth's rotation, because it provides us with additional speed. Hence, we have more energy that can obviously to overcome the Earth's gravitational force. If you found this video useful in explaining these kind of exam questions, please like and subscribe. I'll see you next time. Thank you for listening.